picture a river, just, crystal clear. No murky green algae, no floating plastic bottles,
Right.
no oily sheen on the surface. Visually, it just looks absolutely pristine. But underneath the surface, thousands of fish are literally suffocating to death.
It's the ultimate environmental paradox, right? Because you look at it and you just assume it's healthy.
Yeah.
But biologically,
Mm.
it's a graveyard.
Exactly. And the culprit isn't like some toxic green sludge. It's just water. But it's warm water. A nearby power plant basically used that river to cool its machinery and then pumped the clean but highly heated water right back out.
Which triggers this really devastating mechanism. Warm water, just purely physically, cannot hold as much dissolved oxygen as cold water.
Wow.
Yeah, so as the temperature spikes, the oxygen basically bubbles out, and the fish literally drown in a perfectly clear river. It's called thermal shock.
And that completely shatters our standard mental model of what pollution looks like, I think. We're so used to looking for the obvious symptoms, like the jagged white line on an X-ray. But in environmental science, the X-ray machine is often broken.
Oh, totally. We are looking at a diagnostic landscape for our planet that is just incredibly complex.
It is the absolute definition of muddy waters. You really have to look past the visible symptoms and, understand the underlying chemistry and biology.
Oh, absolutely.
And so that is exactly why we are here today. Welcome to this deep dive. We are speaking directly to you, the relentlessly curious learner, and perhaps specifically the AP Environmental Science student gearing up to absolutely crush the Unit 7 tests.
Yes, you've got this.
We've taken this massive mountain of class notes, flashcards, textbook chapters 14 and 15, and our mission today is to weave them all together. We're going to trace the actual journey of pollution from the water we drink to the air we breathe.
Right. So you don't just memorize terms, but actually understand the mechanisms behind them. Because when you understand how the machine breaks, you don't need to rely on rote memorization anymore.
Yeah, exactly. The vocabulary just makes sense. So let's start right at the source of the problem. If you want to fix water pollution, you first have to figure out how it's getting into the water, right?
Makes sense.
And that brings us to the crucial distinction between point and non-point source pollution, which is, a huge concept.
Oh, it is the absolute foundation of environmental regulation. You have to know this.
So think of it this way. Point source pollution is like catching someone red-handed pouring a 2-liter bottle of soda directly into your prize-winning fish tank.
I love that analogy.
Right. It is a distinct, identifiable location, a specific wastewater pipe discharging from a chemical plant, or a ditch draining directly from an industrial facility. You can literally point your finger right at it.
Which makes it highly actionable.
Yeah.
From a legal standpoint, you know exactly who owns that pipe. You can mandate a filter, you can issue a fine, or you can just shut them down.
But non-point source pollution, that is a logistical nightmare. That is like trying to figure out exactly who brought a cold to a massive, crowded indoor concert.
Good luck with that.
Yeah, it's completely diffuse. We're talking about fertilizer runoff from an entire farming community or oil washing off an endless suburban parking lot during a rainstorm. You can't point to one single pipe, which means, you can't easily regulate it.
And what's really fascinating here is the economic reality driving this whole thing. When we talk about these diffuse sources of pollution, we run into a major economic concept. It's called an externality.
Okay, let's unpack this because this is a term that trips up a lot of people. How does, economics play into a polluted river?
It basically comes down to how we price things. So an externality is a cost of a human activity that isn't factored into the price of the goods we buy. Let's say a factory dumps dye into a river to make, cheap $5 t-shirts. The cost of cleaning that river, the loss of the local fishing industry, the decline in public health, none of that is reflected in the $5 price tag.
Oh, wow. So the buyer gets a cheap shirt, the seller makes a profit, but society as a whole subsidizes the true cost by just living with a destroyed river.
Precisely. The cost is external to the transaction. That's why it's an externality.
That makes so much sense.
And until regulations force companies to internalize those costs, by making them buy expensive filtration equipment, pollution will always be the cheaper, easier business decision.
That is a massive concept to grasp. Definitely write that down. So pollution comes from specific points or diffuse areas driven by these economic loopholes. But let's look at what actually ends up in the water. I want to push back on a common misconception here.
Okay, lay it on me.
When we talk about human wastewater, right? Sewage, gray water, organic waste, animal manure. A lot of people think, well, it's gross, obviously, but it's natural. It's not some synthetic chemical. So why is it so catastrophic for a river?
It's a very logical question. And the danger isn't that the sewage itself is highly toxic in a chemical sense. The danger is a biological chain reaction.
Hmm.
To understand it, you have to understand BOD.
Biochemical oxygen demand.
Exactly, biochemical oxygen demand.
Walk us through the mechanism of that chain reaction. Like, what is actually happening in the water?
So when a massive influx of organic waste enters a waterway, it acts like an all-you-can-eat buffet for naturally occurring decomposers,
Hmm.
primarily bacteria.
Right.
They feast on the waste, and their populations just explode exponentially. But here's the catch. To metabolize all that waste, these decomposers need to breathe. They consume the dissolved oxygen in the water.
Wait, so a high biochemical oxygen demand means the water is literally being starved of oxygen by greedy bacteria?
Exactly. The decomposers suck the oxygen out, and the larger aquatic life, the fish, the crabs, the amphibians, they just suffocate.
That's horrifying.
It is. This creates what we call dead zones. And the most famous one in the United States is the end of the Mississippi River down in the Gulf of Mexico.
Right, because millions of acres of farming heartland drain all that nutrient-rich runoff down the river.
Yep, causing massive bacterial blooms that strip the Gulf of oxygen. Another big example is the Chesapeake Bay, where oxygen-depleted waters routinely devastate the crab populations. It's a total domino effect.
Now, obviously, we want to know if our local water has been contaminated with this kind of human or animal waste, but I mean, we don't sit around testing the water for every single rare disease, right? We look for a red flag.
Right, you look for an indicator species.
And if you are studying for the test, underline this term, fecal coliform bacteria.
Specifically E. coli.
Yes. E. coli isn't always deadly itself, but it thrives in human and animal intestines. So if you find E. coli in a river, it is a glaring neon sign that raw sewage is present. And therefore, the really dangerous pathogens like cholera or typhoid are probably there too.
And to prevent this, we have engineered interventions. In rural areas, homes use a septic system. It's essentially an underground tank where the heavy solids settle to the bottom.
To be broken down by bacteria.
Right. And the relatively clear liquid at the top slowly filters out into a leach field where the soil naturally purifies it.
But in a dense city, a leach field isn't going to cut it. You need a municipal sewage treatment plant. And it's crucial to understand the two main steps there.
Primary and secondary.
Exactly. Primary treatment is just physical removal. It's screens and settling tanks that catch the floating plastic and the heavy grit. But secondary treatment, that is a biological process.
Right. They basically pump oxygen into massive vats of wastewater to intentionally speed up those hungry bacteria we talked about earlier, letting them eat the organic waste in a controlled environment before the water is sterilized and released.
But humans aren't the only ones producing staggering amounts of waste. We also have to consider CAFOs, concentrated animal feeding operations.
Oh, industrial agriculture.
Yeah.
Yeah, we're talking about facilities packing thousands of cows or pigs into tight quarters, generating literal tons of manure.
And they store that highly concentrated waste in massive open-air pits called manure lagoons.
Which is just as lovely as it sounds.
Oh, I'm sure. But if the lining of that lagoon tears, or if, like, a severe storm causes it to overflow, an unimaginable amount of high BOD waste floods into local waterways.
Instantly triggering those suffocating dead zones.
Okay, so that is the biological side of the equation. Let's look at the chemical invaders, the heavy metals. There are 3 heavy hitters that consistently show up in environmental diagnostics. First is lead. Now, we all know the tragedy of the Flint, Michigan water crisis, but it's really important to understand how it happened. It wasn't just that they had old lead pipes.
Right, it was a massive chemistry failure. Millions of homes have old lead service lines. But normally, municipal water is treated with specific anti-corrosive chemicals that build up a protective scale, basically a mineral coating on the inside of the pipe.
Oh, so it acts as a barrier between the water and the lead.
Exactly. But in Flint, when they switched their water source to the highly acidic Flint River, they failed to add those corrosion inhibitors. The acidic water literally dissolved that protective barrier away, stripping raw lead straight from the pipes into the drinking water.
And lead is a potent neurotoxin. It causes irreversible cognitive impairment and severe neurological issues, particularly in developing children.
It's tragic. Now, the second major metal is arsenic. While it can occur naturally as rocks weather over time, human activity vastly accelerates it, particularly through mining.
Oh, right. When miners blast through rock to get to coal or precious metals, they often expose a mineral called pyrite. Fool's gold.
Yes. And when pyrite interacts with air and water,
It creates a chemical reaction that produces sulfuric acid, right?
nailed it. This is known as acid mine drainage. That highly acidic runoff acts like a chemical solvent. It leaches toxic metals like arsenic out of the surrounding rock and washes it straight into our groundwater aquifers.
Which brings us to the third metal, mercury. And this one is a fascinating example of how our environmental systems are just completely interconnected. Because if I am eating a piece of tuna and I get mercury poisoning, it's wild to think that the mercury likely came from a rock being burned hundreds of miles away.
It is the ultimate cross-contamination. The vast majority of mercury pollution doesn't actually start in the water. It starts in the air.
Wow.
Yeah, when we burn coal in power plants, trace amounts of mercury trapped in the coal vaporize and go up the smokestack. It rides the wind currents, and eventually it just rains down into our oceans and lakes.
But it doesn't just sit there.
No, once it hits the aquatic sediment, specific anaerobic bacteria actually alter its chemistry. They convert this airborne elemental mercury into methylmercury, which is highly toxic and really easily absorbed by living tissue.
And this triggers a critical ecological mechanism. If you are learning these concepts, you absolutely must know the difference between bioaccumulation and biomagnification.
Yes, they sound similar, but they operate on completely different scales.
Walk us through it.
So bioaccumulation is the story of a single organism. It's the buildup of a toxin-like methylmercury in an individual fish over its lifetime. The fish absorbs the chemical faster than its body can excrete it, so as it ages, it just gets more and more toxic.
Okay, so bioaccumulation is the individual. Got it.
Right. Biomagnification, however, is the story of the entire food chain. Think about a tiny plankton absorbing a microscopic amount of mercury. Then, a small fish eats thousands of those plankton, absorbing all of their combined mercury.
Right, and then a bigger fish eats hundreds of those small fish.
Exactly. By the time you reach an apex predator, like an albacore tuna or a bald eagle, the concentration of the toxin has magnified exponentially.
And it isn't just heavy metals that biomagnify. Humans have engineered an entirely new class of chemicals that do the exact same thing: synthetic organics.
Ah, yes.
These are human-made compounds: pesticides, pharmaceuticals, hormones, industrial chemicals like PCBs.
And many of these fall under the umbrella of POPs, persistent organic pollutants. Also things like PBDEs, which are flame retardants.
Now, why do they persist? Like, why doesn't nature just break them down over time?
Basically because nature has never seen them before.
Mm.
They are held together by incredibly strong carbon-halogen bonds that natural bacteria simply do not have the enzymes to digest.
Oh, wow.
Furthermore, many POPs, like those flame retardants or the pesticide DDT, they are fat-soluble. They don't dissolve in water. They dissolve in lipid tissue. So once they enter an animal, they just lock into the fat cells and stay there, biomagnifying right up the food chain.
It's a terrifying piece of chemistry, honestly. And speaking of chemistry that doesn't mix well with water, let's talk about oil spills. When a disaster like the Exxon Valdez or the BP Deepwater Horizon happens, I mean, the visual is horrifying.
Yeah, and the cleanup methods are equally complex. You generally have two options. You have physical remediation, like deploying containment booms.
Those are the giant floating barriers, right?
Yeah, they corral the oil on the surface so it can be physically skimmed off.
Yeah.
But often, the sheer volume is just way too much, so we turn to chemical dispersants.
Now, I always assumed a dispersant basically destroyed the oil, like deleted it.
That is a very common misconception. Dispersants don't delete the oil. They act very much like the dish soap in your kitchen sink.
Oh, okay.
They are molecular surfactants with a hydrophilic head that loves water and a hydrophobic tail that loves oil. They attach to the giant oil slick and rip it apart into billions of microscopic droplets.
So it just kind of disappears from the surface.
Exactly. It sinks into the water column. It stops the oil from washing up on the beaches and smothering the birds, which is good, but it dramatically increases the toxicity of the water for the deep-sea marine life. It's a massive environmental trade-off.
Wow. Okay, so we've covered biological, chemical, and physical pollution. Wait, actually, let me quiz you on a few more physical ones.
Now, bring it on.
What about sediment pollution? Just dirt from construction or logging? Why is that actually bad?
Oh, that's a big one. It makes the water cloudy, which blocks sunlight. And if sunlight can't penetrate, plants can't photosynthesize. Plus, it physically clogs fish gills.
Nice. And we already covered thermal pollution? Oh, what about noise pollution?
Right, like ships and submarines.
Yeah.
The loud sonar and engine noise interferes with animal communication, especially for marine mammals like whales that rely on echolocation.
Perfect. Okay, so how do we actually govern all of this? We have two massive pieces of legislation in the U.S. that draw the battle lines.
First is the Clean Water Act of 1972. It is vital to remember that this act is primarily concerned with surface waters.
Surface waters. Got it.
Right. Its goal is to make rivers and lakes safe for fish, shellfish, wildlife, and human recreation. It regulates what comes out of those point source pipes we talked about earlier.
But if you're talking about the water coming out of your kitchen tap, you are looking at the Safe Drinking Water Act. This law empowers the EPA to set strict national standards for our drinking water. Specifically, they establish what are called MCLs, maximum contaminant levels.
The EPA essentially looked at the data and drew a hard line in the sand for 77 different substances, stating exactly how many parts per million of, say, arsenic or lead are legally allowable before a municipality gets shut down.
MCLs. Keep that acronym in your pocket for the test.
Definitely.
All right, now let's follow the water cycle. Water evaporates, it rises, and it takes us straight into our next diagnostic frontier. We are opening up chapter 15 and looking up into the atmosphere.
The sky is a completely different beast, but, it operates on very similar principles of chemistry.
Under the Clean Air Act, the EPA established NAQS, which are the National Ambient Air Quality Standards, for what are universally known as the 6 criteria air pollutants.
The big 6.
Why these 6? Because historically, they were the most ubiquitous, widespread drivers of severe health crises and agricultural damage across the country. You absolutely need to know them.
Write these down, seriously.
Sulfur dioxide, nitrogen oxides, carbon monoxide, particulate matter, lead, and tropospheric ozone.
And to make sense of how they behave, you really have to categorize them. You have primary pollutants and you have secondary pollutants.
Right. Primary pollutants are the direct offenders. They are emitted completely formed from a specific source. Like when a coal plant burns fuel, sulfur dioxide shoots straight out the smokestack. When you turn on your car, nitrogen oxides and carbon monoxide pour directly out of the tailpipe.
But the atmosphere is not just an empty void holding these gases. It is a turbulent, highly energetic chemistry lab. Secondary pollutants are formed when those primary pollutants get into the sky and start reacting with sunlight, water vapor, and oxygen to synthesize entirely new, often more dangerous compounds.
And the undisputed star player of secondary pollutants is ozone. I really have to emphasize this because it is a trap so many people fall into on the exam. Listen to me. Your car does not emit ozone.
Yeah.
Say it again for the people in the back.
Your car does not emit ozone. Your car emits nitrogen oxides or NOPACs. Those primary pollutants float up into the air, they bake in the intense sunlight, and they mix with VOCs, volatile organic compounds.
Like fumes from gasoline.
Exactly. VOCs are things that easily evaporate at room temperature, like gasoline fumes, paint thinners, formaldehyde, or even natural pine tree sap.
So you have no NOx plus VOCs thrown into the oven of sunlight. And that specific chemical recipe creates ground-level ozone.
Which is the primary ingredient of photochemical smog, that toxic brown haze hanging over cities like Los Angeles, or Beijing.
Yeah.
It is highly corrosive. It triggers violent asthma attacks in humans, and this is wild. It is so oxidative that it actually burns and damages the cellular structure of plant leaves, devastating crop yields.
Which leads us perfectly to the next catastrophic secondary pollutant. Acid deposition, better known as acid rain. Let's look at the actual equations because these are must memorize for the test.
Yep. It traces back to our two big primary pollutants, sulfur dioxide, or SO2, primarily from burning coal, and nitrogen oxides, NOx, primarily from burning gasoline.
Okay.
In the atmospheric chemistry lab, sulfur dioxide reacts with atmospheric water vapor to form sulfuric acid. The equation is basically SO3 plus H2O yields H2SO4. Meanwhile, nitrogen oxides react with water to form nitric acid. NOx plus H2O yields HNO3.
And when that rains down, it dramatically lowers the pH of lakes, disrupting the reproductive cycles of fish. But even worse, just like the acid mine drainage we discussed earlier, acid rain hitting the soil acts as a solvent. It leaches naturally occurring toxic metals like aluminum out of the dirt and washes them straight into the waterways.
Fortunately, we have engineered pollution control technologies to fight this. One of the most effective is the wet scrubber, installed directly inside the smokestacks of coal power plants.
How does that actually work?
It's pure chemistry. Before the exhaust gases can leave the smokestack, they are sprayed with a liquid mixture of water and limestone, calcium carbonate.
Okay, so a wet spray.
Right. The limestone chemically reacts with the acidic sulfur dioxide gas, neutralizing it and turning it into a heavy, solid calcium sulfate sludge that just drops to the bottom, completely removing the sulfur before it ever hits the air.
That's brilliant. Other technologies include electrostatic precipitators, which use an electrical charge to magnetically pull particulate matter out of the exhaust, or baghouse filters, which basically act like giant industrial vacuum bags.
Right, we trap the pollution before the chemistry lab in the sky can get its hands on it.
Exactly. But we really need to address a massive point of confusion regarding the sky. We need to talk about the ozone layer.
Ah, the tale of two ozones. Because context is literally everything here.
It really is.
Tropospheric ozone, the stuff down here at ground level that we just talked about, is terrible. It's smog. It damages your lungs. But stratospheric ozone located miles up in the upper atmosphere is essential for life on Earth. It is our planet's chemical sunscreen. It absorbs lethal UVB and UVC radiation from the sun.
There's this brilliant analogy floating around the environmental science community. Stratospheric ozone depletion is essentially the Kobe Bryant of environmental science concepts.
I love this framing so much.
It makes perfect sense. Kobe was universally famous, and the hole in the ozone layer was the most famous, universally recognized environmental crisis of the 1980s and 90s. We were using synthetic chemicals called CFCs and refrigerants and aerosol hairsprays.
Right.
They drifted up to the stratosphere where the sun's radiation broke off their chlorine atoms, and those rogue chlorine atoms basically acted like Pac-Man, just ripping apart the protective ozone molecules.
It was a terrifying global threat, but, we largely addressed it with a global treaty called the Montreal Protocol, phasing out those CFCs.
But the fame of the crisis remains. Because it's so incredibly famous, if you give a student a tricky multiple-choice question about urban air pollution, they panic and just guess stratospheric ozone depletion. They just throw Kobe at the problem.
Yes, I see it all the time.
Do not do this. Stratospheric ozone depletion does not cause global warming, it does not trap heat, and it doesn't irritate your lungs down here on Earth. Only guess it if we are specifically talking about UV radiation, skin cancer, or CFCs.
Keep your atmospheric layers separated, guys.
Let's bring things out of the sky and actually step inside. Because the diagnostic landscape doesn't stop at your front door. Indoor air pollution is a massive, often totally invisible threat.
And the nature of that threat depends entirely on where you live. In developing nations, the primary indoor hazard is the combustion of biomass. Families rely on burning wood, animal manure, or cheap coal inside their homes for heating and cooking, often with little to no ventilation.
That sounds dangerous.
It is. This creates a lethal daily exposure to heavy particulate matter and carbon monoxide.
Carbon monoxide. That is an incredibly insidious primary pollutant resulting from incomplete combustion. You can't see it, you can't smell it, but its mechanism of action is deadly. It binds to the hemoglobin in your red blood cells with an affinity roughly 200 times stronger than oxygen.
Wow.
It essentially locks oxygen out of your bloodstream. You just peacefully fall asleep and suffocate.
Meanwhile, in highly developed nations, our homes are sealed super tight to save on energy costs, which creates a whole different set of problems.
Sick building syndrome.
Right. We deal with VOCs, off-gassing from formaldehyde in our carpets and presswood furniture, and we deal with radon.
Where does radon come from?
It's a naturally occurring, highly radioactive gas. It is produced by the natural decay of uranium deep in the bedrock beneath our homes. Because it's a gas, it seeps up through micro cracks in a home's foundation, trapping itself in basements.
Oh, wow.
Yeah, it is actually the second leading cause of lung cancer after smoking.
That's terrifying. And finally, asbestos. An incredibly effective, heat-resistant mineral fiber that was used for decades as insulation. But when those materials age and begin to flake apart, microscopic needle-like fibers become airborne.
And if you inhale them, they lodge deep in the lining of your lungs, causing massive scarring and a specific aggressive cancer called mesothelioma.
It is a stark reminder that some of our most dangerous pollutants were originally engineered to be miracles of modern convenience.
So true.
All right, we have covered incredible ground today. But before we wrap up, let's do a rapid-fire vocabulary sprint. Just the absolute most important terms from both chapters. You ready?
Born ready. Let's do it.
Externality.
A cost of a transaction that society pays for, like pollution, which isn't included in the product's price.
Perfect. BOD. Biochemical oxygen demand.
How much oxygen bacteria need to break down organic waste. High BOD means dead zones.
Point versus non-point source.
Point is a specific pipe. Non-point is diffuse runoff, like a whole city's parking lots.
Bioaccumulation versus biomagnification.
Accumulation happens in one individual over its lifetime. Magnification happens across the entire food chain, ending at the apex predator.
MCLs, maximum contaminant levels.
The EPA's hard limits for pollutants in drinking water under the Safe Drinking Water Act.
Primary versus secondary pollutants.
Primary comes straight from the source, like an exhaust pipe. Secondary forms in the atmosphere through chemical reactions.
And lastly, photochemical smog.
Ground-level ozone created when NOx and VOCs bake in the sunlight.
Crushed it. From the economics of externalities, to the suffocating mechanism of BOD, to the chemistry of acid rain, and the hidden dangers of indoor air. But, before we sign off, I want to go back to something we talked about earlier, the coal scrubbers.
Ah, right, the technological fix for sulfur dioxide.
Exactly. We spray the limestone, we trap the sulfur, we keep the air clean. I mean, it sounds like a total victory.
It does. But we have to remember the fundamental law of conservation of mass. Matter cannot be created or destroyed. It only changes form.
So, if we scrub the sulfur out of the exhaust, where does it go?
It doesn't vanish.
Ugh.
The scrubber turns that toxic gas into a highly concentrated, heavy liquid or solid sludge. A waste product that power plants now have to scrape out, load onto trucks, and essentially bury in massive lined landfills or unlined holding ponds. So the question I want to leave you with as you mull over these concepts and prep for your exams is this. With many of these advanced control technologies, are we ever truly eliminating pollution? Or are we just perpetually playing a massive environmental shell game, just shifting the toxic burden out of the air we breathe, only to bury it in the soil and water we rely on?
That is a phenomenal, slightly terrifying question to end on. Because everything is connected. Good luck making sense of all your notes. Keep questioning the systems around you. And remember, when it comes to diagnosing our planet's health, nothing is as simple as it looks on the surface. Catch you on the next deep dive.